evening. Welcome. Thank you so much for coming out. We have a really great crowd tonight. We have a full house here and people in the overflow room. We really appreciate it. For those of you who don't know me, I'm Dr. John Mulchaey. I'm the director of the Carnegie Observatories, which is located in Pasadena, California. And by the end of tonight, you're going to know all about the important role that the observatories have played in the history of astronomy. It was 100 years ago this fall that Edwin Hubble showed up in Pasadena to work at Carnegie's Mount Wilson Observatories. And there, as you're going to hear from our first speaker, Marcia, you're going to hear how he used the 100-inch telescope to effectively discover the universe. Unfortunately, as Los Angeles grew, Mount Wilson is no longer a viable site for us to do astronomy. So these days, astronomers like myself work in our facility in Chile, Las Campanas. And so we thought, when Marcia and I were talking about, we invited her out because this was the 100-year anniversary, but we thought we didn't want to leave it at Edwin Hubble. We wanted to talk about, well, what does his universe look like tonight? And so after Marcia talks, I'm going to give a talk about that. So we get to hear kind of the past and the present view of the universe and hear about some of the exciting things we're doing today. So we look forward to that. Then let me tell you a little bit about tonight's speaker so we can get learning all about this exciting astronomy. Marcia Bartusiak. Right? I got it right? Close enough? Yes. We were just talking about the pronunciation. Is an emeritus professor of the practice in MIT's graduate program in science writing. She has written for Science, National Geographic, and Natural History, among other magazines. And she has authored 8 books. Her most recent, a collection of essays called Dispatches from Planet 3, I assume is us, won for her a 2019 Science Communication Award from the American Institute of Physics. And this is actually the 3rd such award she's won from that organization. For the book that inspired tonight's lecture, The Day We Found the Universe, she received the History of Science Society's 2010 Davis Prize for Best History of Science Book for the Public. And I'll just go off script here and say that that's a book that I keep on my desk and I use it all the time when I need to learn more about kind of what happened in my building where I work. Marcia is the world's expert on this. Among the many books on Edwin Hubble, hers is by far my favorite. And I highly recommend you'll hear a bit of it today. You get kind of the Cliff Note version today. Anyhow, what was I saying? I have to keep going here. So she's really built in a very impressive career communicating science with the public, and so this is going to be a really great treat tonight. Help me welcome Marcia to the stage. I'm going to stand over here. I get a seat on the stage. Good.
Thank you so much, John. I'm honored. And I'm honored to be here. And we're here to talk about galaxies. Now, you might have the thought that, well, Hubble discovered that in the early 20th century. That was when we first knew. No. The talk of other galaxies is actually very old. Immanuel Kant, the philosopher, in the 18th century spoke of other island universes. And the great British astronomer William Herschel, he also had the idea that many of the nebulae that he was seeing through his telescopes, which were the best of the day, were also other galaxies. But by the 19th century, things started to change. There was one particular astronomer, James Keeler, at the Lick Observatory, at the end of the 19th century, started looking hard at all of these spiraling disks in the sky. He was focused on this one, and then he would take the photograph and pick out other spiraling disks, and he started counting them. And he came to the idea and the understanding that, no, they weren't separate galaxies. They were baby solar systems in the making, which makes sense. It does look like there's a sun starting to form with the planetary disk and the planets starting to coalesce. So that was the idea when the astronomers in the early 20th century started thinking about what these spiraling disks were. So, Keeler, unfortunately, died an early death, so he was not able to continue this project. But later, In the 1910s, another Lick astronomer, Heber Curtis, decided to further study these spiraling disks. And he didn't use a refractor. There was a telescope at Lick that was one of the largest in the day. He used this smaller telescope known as the Crossley, which consisted of a mirror, which was unusual at that time. Astronomy was mainly done with lens telescopes at that time. It had been brought over from England, and he completely refurbished it, looking like a gun on a naval battleship. Curtis was the man who almost discovered the universe. He surveyed the sky with the Crossley and discovered millions of those disks across the celestial sky. Moreover, he came to believe they really were galaxies, and he did this through some snooping and sleuthing. He photographed some edge on, like this. You can see these dark lanes of gas and dust. And he says, that's just like the dark lanes that we see in the Milky Way galaxy. So he made that comparison. And he also went on to see that sometimes new stars, novae, would appear in some of these spiraling disks. And he said, they're probably just like the novae in our Milky Way, but they're far, far dimmer. He did a comparison. He said, if they are truly novae, these little spots here, then they must be millions of light years away. They must be other galaxies. The problem was, it was all circumstantial evidence. He didn't have a slam dunk. He didn't have a distance measurement out to that spiraling disk. And that's what he needed, and he didn't have it. But fortunately, in that very same decade, there was a woman, Henrietta Leavitt, at the Harvard College Observatory. She found a way to start making measurements out beyond the Milky Way. She was able to establish a distinct link between the brightness of a variable star. That's a star that brightens and then dims in a very regular fashion. And she saw that there was a link between the brightness and the period, as witnessed by this image here. The bigger the star, the slower the period. The smaller the star, the quicker the period. And she made this graph here showing that relationship. So that meant that once the scale was calibrated, you could look up in the sky, you'd see a Cepheid going bright and dim, sometimes over a period of days or weeks or even months. And then you could say, okay, now I know the brightness if I was right next to it. But, of course, it's dimmer here on Earth, but then you can just, using the law of optics, you can work out how far away it must be to be that dim. Here she found the cosmic yardstick that astronomers were looking for. Now they could make measurements far more distant than they ever could before. They finally had a tool to measure distances beyond the borders of the Milky Way. Well, one of the first to carry out this new technique was this man, Harlow Shapley, who grew up in Missouri. He worked as a crime reporter, of all things, when he was a teenager, and then went on to the University of Missouri, where he majored in astronomy, and then on to Princeton, where he got his doctorate. And once he graduated, he went to the new Mount Wilson Observatory, where he put Henrietta Leavitt's standard candle to good use. He was one of the first to take advantage of this new rule. And what he did was he measured the distances to the many globular clusters that form sort of form like hover around the Milky Way galaxy like bees around a hive. And he measured the distances to all those different globular clusters. It was quite an endeavor. And in this way, he discovered that the Milky Way was far bigger than anyone had previously imagined. In fact, he had at one point liked to say, and he also at the same time noticed that the sun was not at the center of the Milky Way. We had always assumed up to that point that the sun was the center of the Milky Way, just as we had once thought that the Earth was the center of the solar system. But he noticed that it was really off to the side, right there. We're about 2/3 of the way over. Shapley liked to say, the solar system is off center and consequently man is too. That was around 1918. And I said, he noticed that the Milky Way was far bigger. It was previously thought to be 30,000 light years wide, but he turned that into what we now know is 100,000 light years wide. This was a huge leap in size. In fact, so big that he came to think of the Milky Way as the universe. It was his big galaxy model. The universe, the Milky Way was the universe, and all of those little spiraling disks, they were just little appendages. So he had that and really, really championed that model. So by 1920, there were two completely different models of the universe. There was Shapley with his big galaxy model, and there was still Heber Curtis over at Lick championing the fact that there were other galaxies, other Milky Ways, other island universes. It got to be such a tussle, they even had a great debate right here in Washington, D.C. in 1920. But at that time, the evidence was still muddled, and no one really won the debate. Now, Curtis could have continued his work at Lick and finally come around to proving that the galaxies that he was seeing in the sky, all those disks he was seeing in the sky were galaxies. But he went on to accept a directorship at the Allegheny Observatory, right outside Pittsburgh, Pennsylvania. When you can imagine, the steel mills were putting out smoke and dust and gas. He never had another good day of astronomy after that, and he knew it. And so off he went. It could have been the Curtis Space Telescope, but no. Shapley, he was the Cepheid variable expert. He could have gone on and searched for Cepheids out in those spiraling disks, but did he? No, in fact, there's a story at Mount Wilson that an apprentice astronomer had been working on the telescope and he did a plate of the Andromeda Nebula and thought he saw a variable star in one of the plates. And he circled it with a grease pen, ran to Shapley, showed him the plate and said, I think I found a Cepheid variable in the Andromeda Nebula. Shapley looked at it and told him all the reasons he was wrong, took out a handkerchief and wiped out the grease marks and didn't want to deal with it. He was wedded to his model of the big galaxy. The Milky Way was the universe. So much for Shapley. It could have been the Shapley Space Telescope if he had listened to that observer. So that left the field wide open for this newcomer who arrived at Mount Wilson straight from serving as an Army major in World War I. The observatory's director, George Ellery Hale, was always on the lookout for good people, and he was aware of Hubble's PhD work at the University of Chicago and promised him a job once he came back from the war. So when he did show up, Hubble at first stood in Shapley's shadow. At that time, Shapley, who had resized the Milky Way, found that we weren't at the center, he was the golden boy of astronomy. But by 1921, Shapley went off to take over the directorship of the Harvard College Observatory, and so Hubble was then able to solely focus on the spiral nebulae. Now, Hubble was a very complex man, a bit aloof with his colleagues. Friends called him an Adonis. He was fairly good looking. I always think he looks like a young Jeremy Irons when, he grew up in the Midwest, strong middle class roots. His father was in the insurance business, and he went to the University of Chicago for undergraduate work, hoping to major in astronomy, which was a childhood passion. But his father insisted he have a profession, a respectable profession like law. So he studied law. He did so well in college that he got a Rhodes Scholarship upon graduation and went to Great Britain for 3 years at Oxford University. And there he completely transformed himself. He began to speak with a British accent, which he kept the rest of his life. He learned to brew a proper cup of tea, wore a black cape with great flourish. He yearned, and this was his favorite observing outfit, the knickers. He would always show up at Mount Wilson with his knickers to do his observing. He was also someone who yearned to be singular and distinct, even adding a bit of dishonesty to his resume. He always told people, because he had studied the law at Oxford, that he had given up the law to go into astronomy. But the fact is, once he got back from Oxford, he went to his hometown and he taught at the high school for a year, teaching physics and Spanish. Never, ever dealt with the law. But he did, after that high school year, finally achieve what he had longed to do, and that was start his PhD at the University of Chicago, where he specialized. He did have a good nose for important problems, and he knew that the mystery of the spiral nebulae, what were they? What was their relationship to the universe? He took that on as his graduate thesis. So upon graduation, and after the war, he showed up on September 11th, 1919, just a week after the world's largest telescope was in full operation. And he began using the 100-inch on Christmas Eve that year, and he kept this logbook. This is the 100-inch logbook that he kept to keep track of his observations, page after page. He told a colleague that he was going to, quote, determine the relation of nebulae to the universe. And he did this with single-minded devotion, using both the 100-inch and the 60-inch telescope there at Mount Wilson. Year after year, from 1919 on, plugging away, going from all over the celestial sky, taking pictures of the spiraling disks. Each photograph was labeled, H for 100-inch, the plate number in the sequence, and H for Hubble. You can see that up around in here. Finally, in 1923, He spent 47 nights on the mountain, and that was the year that finally something happened. And I'd like to read a passage from my book to describe that time. October 4th, 1923. The seeing was poor, but it was good enough, just barely, to stalk some celestial quarry that autumn evening. As the giant scope swung around, there was a whine, a series of loud clicks, and then a final clang as the instrument was secured into place. Hubble examined M32, a small and roundish nebula, for a spell, but he then maneuvered the telescope just a fraction of a degree to photograph M31, the famous Andromeda Nebula, the target of choice in the island universe debate. By then, the seeing had deteriorated to a point that other astronomers might have closed up shop. But Hubble persevered, and despite the mediocre viewing, soon noticed a new speck of light within Andromeda's cloudy veil. It was exactly what he was hoping to find one day as he conducted his extensive survey of the nebulae. Novae had been seen before in Andromeda. That wasn't startling. But Hubble was sure that additional sightings would help reveal Andromeda's secret. Nova suspected, Hubble neatly wrote in black ink in his logbook for plate H331H. After photographing Andromeda for 40 minutes, he went on to observe another nebula, a barred spiral before ending his run. He returned the next night and again saw the new pinpoint of light. Confirms Nova suspected on H331H, he wrote in his logbook. Well, here's the famous and actual photograph of his night on the mountain. Once he got back to his office, he started comparing this photograph with other photographs that were in the archives there at Mount Wilson. And by doing that, he figured out that, yes, indeed, he spotted some additional novae, and two of them were definitely never specks that were never seen before. But he found that one was actually a spot, comparing it to other plates, that was brightening and dimming over time. He had found a variable star in Andromeda. He was so excited, you can see he X'd it out, the N, and put in VAR exclamation point. That's how excited. I mean, Hubble was so reserved. To have an exclamation point on the photographic plate, he was excited. He knew he had celestial gold, and here was possibly the cosmic yardstick that he had been looking for. Now, that took more time. There are all types of variable stars. He needed specifically a Cepheid star. So he started keeping track. He'd go to the mountain and keep track of the star's variability. And 3 nights in February 1924 proved crucial. On the 5th, 6th, and 7th of that month, seen here on the right side, this is where his data points are, he directly observed his variable brightening by more than a magnitude. It just went skyrocketing up over those 3 nights. It was a tremendous break because he knew from the length of the period and the overall shape of the curve, he now knew his variable was a Cepheid, a rare type of variable star that's thousands of times brighter than our sun. This, writing that graph and working out all those calculations, that was his moment of discovery. In fact, he went back to his notebook and added a note. Here's from my book. Customarily reserved, Hubble at this moment is unmistakably restive. He didn't write his message in black ink, which he regularly did for his records, but instead in pencil. And his handwriting, usually so fluid and precise, was more hurried and askew. He was obviously elated. On this plate, 3 stars were found, 2 of which were novae, and 1 proved to be a variable, later identified as a Cepheid, the first to be recognized in M31, he wrote. To highlight the addition, he drew a big arrow pointing directly downward at his historic news. In its broad stroke, the arrow makes his excitement visible upon the page. For once, Hubble dropped his guard and figuratively clicked his heels at this moment of discovery. Well, Hubble couldn't help but notify his nemesis, Harlow Shapley. They could not stand one another. Shapley thought Hubble was a snob. Hubble always never wanted to hang out with the Mount Wilson astronomers. He loved intermingling with the Hollywood aristocracy, the actors, actresses, and writers, where Shapley was the down-hole boy from the farm there in Missouri, and Hubble thought he couldn't stand that at all. But they needed one another. Hubble had access to the world's largest telescope, and Shapley, being now director of the Harvard Observatory, had access to the greatest photographic collection, which astronomers often needed to consult. So notice here that Hubble didn't open up with polite niceties or inquiries of health. He got right to the point. Quote, "You will be interested to hear that I have found a Cepheid variable in the Andromeda Nebula." He then went on to describe all the technical details. Had a period of 31 days, varied between magnitude 18 and 19. And here's the kicker. Using the very same formula that Shapley used on his globular clusters, Hubble calculated the distance out to Andromeda. He calculated at that time a distance of 1 million light years, which was definitely far beyond the borders of the Milky Way. We now know it's it's better calibrated now. We now know it's more than 2 million light years, but still, it was definitely, Andromeda was outside the Milky Way. It was another galaxy. No more circumstantial evidence or convoluted reasoning. Here was a direct, indisputable measurement out to Andromeda. Well, Hubble got in some further digs. At the end of the letter, quote, "I have a feeling that more variables will be found by careful examination of long exposures. Altogether, the next season should be a merry one and will be met with due form and ceremony." Well, Shapley, upon receiving this letter, held it up in his office and told a colleague then in the room, "Here is the letter that has destroyed my universe." He knew right away that game was over. No more big galaxy model. Well, Hubble made that finding in February 1924, yet he held off publishing. Why? I mean, today, boy, that would be on the internet faster than you could blink. But Hubble's greatest fear, he was a perfectionist. His greatest fear was being caught in a scientific error. And there was a colleague at Mount Wilson, a very respected astronomer, Adrian von Manen, who was saying that he was actually seeing spirals rotate in the sky, visibly rotate. And that would only be possible if they were close by. It would be impossible if they were far away. Now, Hubble suspected that he was doing something wrong, but he just couldn't figure it out right away. And so he waited. He waited to figure out where did von Manen go wrong. And he would have kept on waiting, except that the noted astronomer, Princeton astronomer, the dean of American astronomy at that time, Henry Norris Russell, convinced him he must send a paper to the next American astronomical meeting, the American Astronomical Society meeting. And so that is what Hubble did. Whoops, I'm hitting the wrong button there. There. Hubble sent his paper to the next meeting, which was right here in Washington, and it was presented on January 1st, 1925. Hubble was not present. He had Russell read the paper to the assembled astronomers. And so I like to think of that as the day that Hubble officially, finally, announced the discovery of the modern universe, that the cosmos was brimming with other galaxies as far as the telescope could see. So that is the day we found the universe in a way. So now, as the textbooks have it, Hubble then went on 4 years later to triumphantly discover the expanding universe. Well, that's not quite the way it happened. And I'm here to tell the story. Evidence that the spiral nebulae were actually moving outward had actually arrived much earlier using this 24-inch refractor at the Lowell Observatory in Arizona. And it was due to this man, Vesto Slipher, who was the first to actually obtain the speed of a spiral nebula. He attached this spectrograph to the telescope and carefully obtained a spectrum of the Andromeda Nebula in 1912. So while Curtis was at Lick, imaging all those different spiraling disks in the sky, Slipher was at Lowell measuring their speeds. And he found that Andromeda was coming towards us at 300 kilometers per second. I have to tell you, no astronomer had ever seen a speed like that. Stars in our Milky Way, maybe the highest they saw was 30, 40 kilometers per second. So this was astounding that there was an object in the sky coming towards Earth at 300 kilometers per second. This was an absolutely astounding speed. And by 1917, Slipher continued his work, and he started gathering the speeds of 25 of the most prominent spiral disks in the sky. It was an extremely difficult task because when you put light through a spectrograph, it diminishes the light that you can capture. And so sometimes he'd have to spend 40 nights on the mountain just gathering the photons one by one to gather just one spectrum. Well, he saw eventually the results that a few of the spiraling nebulae were approaching us, like Andromeda. That means they were blue shifted. They were moving towards us so that the light waves get compressed, shorter, made bluer. They're blue shifted. But he found that most of them, this is in 1917, most of them were running away from us. The light waves were getting stretched, made redder. They're redshifted. And this was very interesting. By 1917, given this data, he was starting to agree with Curtis that indeed these were separate galaxies. In fact, he even in a 1917 paper suggested at one point this might suggest that the spiral nebulae are scattering. A little prescient notice of the expansion. This was 1917. Hubble was still getting his PhD and about to go off to war. So we had some nebulae that were approaching us. This was what they were seeing, and that some of these nebulae were running away from us. What astronomers didn't know was there a pattern to this. They couldn't explain it. What was going on? That was the question that needed to be answered, and that's what Hubble did in the late 1920s, by teaming up with Milton Humason, a man that used to be a janitor at Mount Wilson, but started helping out and rose to the ranks to become one of the world's greatest observers. So they were a team. Hubble would get the distances to the galaxies, and Humason became a specialist in getting the spectra to get the speeds. So by 1929, Hubble had gathered enough evidence that he was able to find that definitive pattern. He saw that if you double the distance, you double the velocity. There was a pattern to the way the galaxies were moving outward. What's interesting, though, is that the distance information was gathered by Hubble, but Humason was just starting on his velocity information. None of those velocities were from Humason. They were from Slipher's 1917 paper, and Hubble used them without citation or acknowledgement. Created a little kerfuffle there. His fellow astronomers were not too pleased that he left out Slipher's name. I think really Slipher deserves half the credit. But Hubble, this is what, in the textbooks, this is the moment of discovery of the expanding universe. But Hubble at this point had no idea what was happening. He had no idea that this meant that the universe was expanding. He often said that he left theory to the theorists. The correct interpretation of the Hubble law, as it's called, really belongs to this man, Georges Lemaitre, a Jesuit priest and a mathematical physicist. He predicted what Hubble saw in 1929. He predicted it 2 years earlier in 1927. He wrote this paper in a Belgian journal, and it said the receding velocities of the extragalactic nebulae are a cosmical effect of the expansion of the universe. Space-time was stretching outward and galaxies were going along for the ride. He did this by setting up a cosmological model based on Einstein's relatively recent general theory of relativity. And he got quite excited by this, so excited that he went to a conference in Paris that year, met up with Einstein, and excitedly told him, "Look, what your theory has predicted." And Einstein took a look and he replied, "Your calculations are correct, but your physical insight is abominable." Einstein had his own model of the universe, and it was steady and unmoving, and he would have nothing of an expanding universe. He really disliked that model. So it never went anywhere. I mean, if the greatest physicist in the world tells you that your physical insight is abominable, you sort of don't spread the news. And on top of that, he, published in this obscure Belgian journal that no one talked about, and he was a very modest man. He didn't go around telling everybody what he had discovered. It wasn't until 1930, finally, his obscure journal article was rediscovered and given it its due. And it was then, in 1930, then and only then, that Hubble's data, that pattern he saw, could be interpreted as the expansion of the universe. And I'm very happy to say, finally, just last year, the International Astronomers Union voted to rename the Hubble law the Hubble-Lemaitre law. So Lemaitre gets equal credit. Yay. Now I'm just trying to get the constant to be called the Hubble-Lemaitre constant. the Hubble-Slipher constant. So Slipher gets his credit for the velocity information. And it's very ironic because the man who we most closely identify with the discovery of the expanding universe, he didn't really like the idea. He acknowledged it was the best explanation at the moment, but he actually said it's difficult to believe that this is what's really happening. You have to understand this was the era of quantum mechanics in the 1920s that was overturning physics. And he was worried maybe there's a new law of physics out there that could explain this in another way. He always, in all of his papers, from that point forward until the day he died, he always wrote about the, quote, apparent velocities, just in case some new law of physics snuck in and he wouldn't be caught in an error in his scientific papers. He was a doubting Thomas until the moment of his death. Here in this 1947 paper, he died in 1953, and a few years before that, as he wrote this paper about the new 200-inch telescope that was about to open on Palomar Mountain. We may predict with confidence that the 200-inch will tell us whether the redshifts must be accepted as evidence of a rapidly expanding universe or attributed to some new principle of nature. But the legend lives on. Historians of astronomy Helga Krog and Robert Smith suggest this legend was shaped by American astronomers desiring a founding father and a figure around whom they could drape a single version of the history of the discovery of the expanding universe. But Hubble stood upon the foundation built by many others. Though Hubble does remain, and rightly, the central figure in this legendary story, there are all those astronomers who came before: James Keeler, Henrietta Leavitt, Heber Curtis, Vesto Slipher, Harlow Shapley, and Georges Lemaitre. And let's not forget the grand instrument that made it all possible, the 100-inch telescope at Mount Wilson. Thank you very much.
Hey Siri, let me stop that. Hey Siri, let me stop that. All right, thank you. Wonderful, thank you, Marcia. That was a really, I always love hearing that story. You learn a lot about the way scientists work, for better or worse. I like to think we're nicer now than we used to be, but who knows? So I thought it would be interesting, as I said earlier, to take that jumping point where Hubble basically showed the universe was a universe and say, what does that universe look like today? And I think he'd be pretty amazed if he could be alive today to see just what we know. And so I'm going to start by talking about what was his real accomplishment, and I think the real accomplishment was discovering galaxies, as Marcia said. And so I thought we should start with what is a galaxy. So this is a beautiful spiral galaxy, nearby spiral galaxy. This is what you think of when I say a galaxy, right? And imagine if you could move outside of the Milky Way and look back, this is what the Milky Way would look like. So what are you seeing here? You're seeing a system with about 200 billion stars, about 1 trillion planets, some gas and dust. And the scale, as Marcia mentioned, is about 100,000 light years across. I'll remind you that light travels about 182,000 miles per second. Light could go around the Earth 7.5 times or something in a second, just to give you an idea of how fast light travels. And yet it would still take 100,000 years to cross a galaxy. These are huge and tremendous systems. But of course, what you see with your eye is not all that's there. And this is due to some another very famous Carnegie astronomer, many of you know, Vera Rubin and Kent Ford, who about 50 years ago showed by studying the motions of the stars in the outer part of galaxies that in fact the motions were much, much faster than they should be, which implies the presence of a much stronger gravity and the presence of more material. And we call that material dark matter. It's still one of the biggest mysteries in astronomy. But based on our current studies, we know that when you see a galaxy like the Milky Way, you're only seeing about 5% of what's really there. About 95% of it is in this dark component. And so this talk's all about, by the way, making you feel really small. and somewhat insignificantly. You should never feel insignificant. You live on a very special planet. In case I don't make that point later, it's a really cool planet. There's just a lot of others. So what makes up a galaxy? As I said, 200 billion stars, about 1 trillion planets. This is a guesstimate. It might actually be low. And about 95% of it is dark matter. The challenge for astronomers since Hubble's time has been understanding how the universe went from starting with the Big Bang to producing these beautiful structures like this. This is just an amazing structure. How did this happen? And thankfully, astronomers are gifted with a time machine by space itself. And that's because it takes time for light to reach us from distant parts of the universe. We can see what the universe looked like in the past. And so we can look at distant objects and nearby objects and see how things have changed. We can study the evolution of the universe. And that's something that I and many others do. So this is many of you will be familiar with this image. This is the Hubble Ultra Deep Field. This is my absolute favorite image in all of astronomy. I never get tired of seeing it. You're going to get tired of seeing it because I'm going to show it about 3 more times. Because I really love this image. So let me explain what this is. About 25 years ago, astronomers decided we'll take the Hubble Space Telescope and stare at a blank region on the sky. That is a region that didn't have any bright stars or nearby galaxies. And integrate away for about 2 weeks. And as you integrate away, you add up the light. It allows you to see fainter and fainter things. And clearly, the region that was blank is not really blank. It's just that there's no bright objects in it. But what you're seeing in this image, every speck in this image, except for about 2, is a distant galaxy. This is where you should feel small because, I'll remind you, that means even the tiniest speck on this image is a galaxy with hundreds of billions of stars and trillions of planets. There's 3,000 in this image. And the scale of this image, if you took your fingers and projected it on the sky and pinched them together, that's about the size of this image. If you look at the number of galaxies in just this image and extrapolate around the sky, there may be as many as 1 trillion galaxies in the universe. That's 1 trillion galaxies with hundreds of billions of stars and trillions of planets. The universe is incredibly immense. But the reason I put this image up here is because this is my time machine image. As I said, it takes time for light from distant objects to reach us, so we're seeing what they look like in the past. The reason why most of these objects are so tiny is not because they're not big, it's because they're very, very far away. In this image, the smaller objects you see kind of in the background there are on average about 10 billion light years away. That means you're seeing what they look like 10 billion years ago. This is effectively an image of the universe 10 billion years ago. I'll remind you that Earth is less than 5 billion years old. This is a picture of the universe 5 billion years before the Earth even existed. That's just amazing, right? The other thing that's great about this image, so we can study these very distant galaxies, and we can try to compare them with the more nearby ones, like this one, and try to see how they've changed over time. Of course, nothing is very easy in astronomy. And in fact, it turns out that it's very complicated. The universe has a lot of processes going on, a lot of different things. But this image alone tells you so much information. And you can see it with your eye. First of all, when I said, what does a galaxy look like at the beginning of the talk, I showed you a beautiful spiral galaxy. If you look at this image, you don't see a lot of galaxies that look like spiral galaxies. There are some. You can find them. Let's see if I can find some here. This little blue guy here, there's one here, there's a nice big one here. So there definitely are other galaxies that are like the Milky Way. But then there's other ones that don't look anything like a spiral galaxy. They look more like footballs or round things. There's one there, and there's a bright orange one up at the top there. So clearly, spiral galaxies aren't the only thing. The shapes of galaxies vary tremendously. But the other thing that may not be apparent at first, but if you look at it, it becomes pretty obvious, is that there's a big range of colors in this image, right? And the colors tell you that there's different types of stars in the galaxies. And that ends up being the complicated part. So what do we know about colors of stars? Well, the color of a star tells you about its energy and its temperature. The more massive a star is, the hotter it will be, and it will produce blue light. So when you see blue galaxies, these are galaxies that are dominated by big, massive blue stars. Blue stars don't live very long. They burn out in millions of years. By astronomy standards, that's very short. In contrast, red stars, which are the coolest stars, are small mass stars, and they live for tens of billions of years. And so they last much longer than the blue stars. Well, when a galaxy forms and stars form, they form out of gas clouds. And these gas clouds produce all these stars together. It produces blue stars and red stars. But what happens is, if you imagine that all of a sudden you stopped forming stars in a galaxy, after a few million years, the blue stars will all die off because they don't live very long, and you're left with red stars. And that's what this image is showing you. When you see a blue galaxy, in this image, that means that's a galaxy that's actively forming new stars, or at least over the last few million years, because those blue galaxies and blue stars wouldn't exist. But if you see a red galaxy, what you're seeing is a galaxy where all the blue stars have died off, and no new stars are being created. So in fact, in astronomy, we now call those red and dead galaxies. And so, in fact, you see a lot of those red and dead galaxies. This one up here I pointed out earlier was one of these examples. These are galaxies that have apparently lost their dust and gas because they're no longer forming stars. And so what will happen in those cases is those red stars will live for tens of billions of years, and the galaxies will just kind of fade away. This image tells you it's very complicated. There's different sizes and shapes of galaxies, and there's these different colors. So what's responsible for this? And that's kind of the challenge for modern-day astronomers. So I'm going to talk about a few of the processes, because this is where the fun starts. So you can't give a talk these days without talking about black holes. So there's an important reason, though, I'm talking about it here, because we believe over the last 10 or 15 years that black holes will play a huge role in that diversity of galaxies you see. So let me remind you what a black hole is. A black hole is just an object with extremely strong gravity where nothing, including light, can escape it. Now, the reason why black holes are interesting for galaxies is not the black hole itself necessarily, but as material swirls in towards the black hole, the gravity is so strong it heats that material up to very high temperatures, and huge amounts of radiation is created. X-rays and various things come off, mostly X-rays, in fact. And the winds and that energy that comes off those black holes can actually effectively blow up a galaxy. They can take that material, the gas, and kick it out and stop a galaxy from forming stars. And so the black holes may play an important role in why we see some of those red and dead galaxies. Now, how do you go find black holes? It turns out we have a lot of great evidence for black holes. This, I'll remind you, is that Hubble ultra-deep field again. I just wanted to point out, when you see an image from the Hubble Space Telescope, you're seeing visible light for the most part, things you could see with your eye. And visible light is usually stars, because stars peak, their temperature peaks, and so most of their radiation comes out invisible. So what you're seeing in this image is just the stars. But as I said, black holes, as the material swirls in towards the black hole, it produces very, very hot temperatures. And most of the radiation from around the black hole is actually in X-rays. So if you take this image, or you take this field on the sky, and point it not with a Hubble Space Telescope, but with an X-ray telescope, you see the black holes. And we've done that. This is data with the Chandra X-ray telescope. What you're seeing here are, in fact, the glow of black holes. Actually, not the black holes themselves, once again, the material around the black holes in that same field. And the reason this is true is because stars don't produce very much X-ray emission. So effectively, all you see with an X-ray telescope are things that are really hot, which is mostly the black holes. So this is once again the same field. Here's the visible light from Hubble. That's the stars. There's the black holes. If you do a careful analysis, you find out that those black holes are sitting at the centers of those galaxies. And so this tells us, in fact, that black hole, there's a lot of them too. There's a lot of black holes on the left there. We now know that pretty much every big galaxy in the universe has one of these black holes at the center. To give you an idea of what these black holes are like, these are not tiny little black holes. These are big black holes. They're 1 million to 1 billion times the mass of the sun. That is, if you took 1 billion suns and scrunched them together, you would get one of these big black holes. These are amazing and interesting objects. And they're obviously very important in galaxies because every galaxy seems to have one at its middle. So an interesting question, though, is when did the first black holes appear in the universe? Because I showed you that image, the Hubble Deep Field image, and already galaxies that were 10 billion light years away already were red. That meant you had to have black holes a long time ago if black holes were important. And it turns out that we have black holes all the way back, almost as far back as we can see galaxies. And this is some work by one of our young astronomers, Eduardo Bonedos. And he's been using our Magellan telescopes at Las Campanas, Chile. I'm going to call that Maxine Singer, our former president's there, because it was under her watch that we built this wonderful facility. Thank you, Maxine. She also hired me, so that's two claps for that. These telescopes that we built in Chile, Eduardo's been using them to search, combined with X-ray data, to look for black holes, and he's found more than half of the very, very early universe black holes. He had the record holder, which you may have heard about a few years ago, over 13 billion light years away. And the universe is only 13.7 billion years old. This meant this black hole existed very soon after the Big Bang. What this tells us is that the galaxies and black holes must have formed at around the same time. I have to say, this black hole, the data is not so interesting. That's why I have this beautiful artist's rendition. It looks much better. The data, this black hole, is about 1 billion solar masses. It's a huge black hole. How did the universe create such a big black hole so soon after the Big Bang? That's a real mystery. And so one thing so about 10 years ago, before Eduardo had this result, I became interested in, well, how do you form big black holes? And the obvious solution was, well, you take small black holes and you put them together, right? Seems obvious. But we had never seen that process. So about 10 years ago, I decided, let me see if I can find small black holes that are in the process of combining. And in fact, so what I did is I said, well, the way to find black holes is to look in the X-ray. I've already told you that. And I was looking for sources. If you could find 2 X-ray sources right next to each other, they might actually be 2 black holes in the process of merging. And we found this one right away, and I'm like, these things look very close on the sky. Maybe these are 2 black holes that are going to merge. The challenge is when you see something on the sky, as we learned from Marcia's talk, you don't know how far away it is. You have to measure a distance. And these 2 objects could be very different distances from us, but just projected to be near each other. And so what I did is, when my colleague found this and sent it to me, I happened to be at Chile at the Magellan Telescope again, and I said, I'm going to take a visible light image of this and see what's there. And I did, and I instantaneously knew I had a Hubble moment. It wasn't quite as spectacular maybe as Hubble's, but it was my Hubble moment, one of a few in my career. What you're seeing in the visible light image are 2 galaxies. These 2 galaxies are associated with those X-ray sources. So in fact, those X-ray sources are black holes at the centers of 2 galaxies. The aha moment for me was this thing here, and this little thing coming out the side. These are called tidal tails. Whenever you see 2 galaxies close to each other on the sky, and they have a string of material coming out the end, this means they likely are interacting. And so I knew that when I saw that right away. That meant these 2 objects, these 2 black holes, are physically associated. They're in 2 galaxies, and they're about to merge. We had found a case of a black hole building up. So I went home, back to Pasadena, and we happened to have at that time one of our young postdocs was TJ Cox, who was the world's expert on studying galaxies that come and combine together. And I said to TJ, he does this on computers, and I said to TJ, I showed him this, I said, can you reproduce this? He said, I've already reproduced this. I have, even without knowing, he said, I have a simulation that looks like that. And I'm like, yeah, do you really? Let's see. Well, he did. This is a complete chance. So this is a computer model that TJ does. You see there's a spiral galaxy. Here comes a second spiral galaxy. Now you see right there when they interact, you can see the tidal tails being created. That was the feature that said aha to me. But the galaxy escapes the first time, but gravity will win in the end. This, by the way, up here in the corner is time in billions of years. So 2 billion years later, gravity will bring that galaxy back down. Fortunately, in the simulation, we don't have to wait very long. And here it comes. And this time you see, in fact, that the 2 come very close and effectively are captured. He had this existing simulation, and there was my data. This was remarkably similar. Now, the fun thing, yes, that's for TJ, not for me. The fun thing is you can run the simulation forward. I can't run my real data forward. And what you see is very soon, we're very close to seeing this will form a single system. And the 2 black holes in the galaxies will form a bigger black hole at the middle. And what you're left with, you went from 2 galaxies to 1. Now, this is interesting for a second reason. Well, first of all, we found a black hole. That's good, being created. But the other thing, am I on still? Yeah, okay. The shape of this galaxy is no longer a spiral galaxy. We took 2 spiral galaxies and smashed them together and ended up with a football-shaped galaxy. It's not so obvious from the simulation. But we believe, in fact, that this is how we form those football-shaped galaxies. When I showed you some of those round galaxies in that image, that deep image, those are systems where 2 galaxies have effectively smashed together. And this is an area where we've had a lot of expertise. Francois Schweitzer, who many of you know, he worked here in the Washington branch for a while and is now in Pasadena, has spent his whole career studying these mergers as well. Now, I know what you're saying. This is all very interesting, John, but how is it relevant to me, right? And the answer is it's very relevant to you because you're going to take place in one of these mergers, as Marcia kind of previewed, in about 4 billion years. Because the Andromeda galaxy is coming flying towards the Milky Way. I should say they're actually both flying towards each other. And in about 4 billion years, the two galaxies will merge. This is a great artist rendition of what the night sky will look like in Chile in 4 billion years. There's a lot of uncertainty in that. Except hopefully we will see this giant galaxy coming towards us. And so our own Milky Way is in the process of becoming an elliptical galaxy in about 4 billion years. And you may ask, what happens when you take 200 billion stars and 200 billion stars and you bring them together in this collision? And the answer is remarkably little. It's kind of disappointing. There's so much space, empty space between stars in a galaxy, that effectively you bring them together and virtually no stars will be impacted by other stars. In fact, the Earth, which will still be orbiting the sun at this time, will continue to orbit the sun most likely. So it's not really a violent collision, but it will be kind of a fun thing to see. You'll just have a lot more stars in your night sky in 4 billion years. Okay, something to look forward to. Now, it turns out that you can also have interactions between galaxies and gas, and this can have a huge impact on a galaxy. This is some work by Stephanie Tomlinson, who was our first NASPRIN fellow. And what Stephanie's been studying is she's been studying what happens if you take a galaxy and it hits a big X-ray cloud. Well, why would there be a big X-ray cloud? Well, it turns out they exist in the universe because of gravity, again. Gravity is always the dominant force for everything. On the left here, you see what we call a cluster of galaxies. This is a collection of thousands of galaxies that have formed in a single gravitational component. These galaxies are kind of all flinging around each other, and they brought all their gravity, all their dark matter together. So these are the most massive systems in the universe. Another area where Carnegie astronomers, Alan Dressler, many of you may know, a very famous guy, he spent his career studying these things as well. And so on the left you see basically those galaxies in the cluster. Because they have so much gravity, though they also bring in gas from the field, falls into the cluster, and because of the gravity, it heats up once again to very high temperatures, just like the black hole case, and it emits X-rays. So in fact, this image here on the right is the same region of space with an X-ray telescope. Once again, the Chandra X-ray telescope. There is a giant mass of hot X-ray gas sitting in this cluster. So now what Stephanie's been studying is what happens if you now drop a galaxy from the outer part and it hits this X-ray cloud. And so she's done simulations that will show you, I'll show you that right now. Okay, so this is you imagine now this is the gas disk in our spiral galaxy. And you have to imagine the disk is falling down into the cluster. And what you see, at some point it will hit the gas, it hit right there. And you see as it hits the gas, the interaction with the hot gas strips the material from the galaxy in these beautiful ways. Basically, effectively, the collision with the hot gas evaporates the gas in the galaxy. And you see, it forms these beautiful tails. Well, why is this relevant? Well, this is relevant because if you take one of those blue galaxies that's forming stars and dump it into this hot X-ray gas, it basically will take out all the gas, and you no longer will be able to form stars. It will turn a red galaxy, blue galaxy, into a red-ended galaxy. And so we actually have found these things now. There's some great examples of it. These are just two of these. We nicknamed them jellyfish galaxies because astronomers always have to come up with names for things. This is a relatively new term. And you see there's the disk of the galaxy, and here's these beautiful tails. This is the material being stripped off by the interaction with the hot gas. And similarly over here once again is the disk, and here's the tail. So this process also impacts the galaxies we see. So now I'm going to return to my Hubble Ultra Deep Field. I've talked about 3 different processes that we know are important. Black holes, which could potentially blow up a galaxy, blow out the material in a galaxy. I talked about mergers, which can change the shape of a galaxy and also change the color, and this gas interaction. So that's just some of the things we've learned over the last 20 years or so. But this image, I kind of did a little bit of I was a little loose, let's just say. I was a little loose earlier when I said that the galaxies you see in this image are 10 billion light years away. What I meant to say is the light that left those galaxies 10 billion years ago. Since then, the universe has continued to expand. So in fact, these galaxies that were 10 billion light years away 10 billion years ago are no longer 10 billion light years away. They're about 30 billion light years away. And so the universe continues to get bigger and bigger. And so this is Edwin Hubble's second kind of result, although I think Marcia made a really good case for how he played a role in this. This is the famous Hubble law, which has now been changed, as she pointed out. This is the relation that showed that things were farther away, were moving faster. I just wanted to show a modern version of this and just point out, I'm not going to go into detail, this goes very much further out. Hubble's data would be the first point on this plot. We can now do measurements of the expansion of the universe much, much further out. And the reason this is interesting is if you concentrate on some of the further away data, this plot here, a very famous plot that led to the Nobel Prize, as I'll explain in a second. If the expansion of the universe was steady, we would have expected the points at very, very far away to fall along this red line. And you can see that the points all fall kind of above the line, or most of them. This was the discovery, and this is the plot that tells you kind of what that meant. What it means is the farther away points were actually moving. The universe was expanding at a slower rate in the past. In other words, the universe is speeding up. It's accelerating. And so this discovery in the late 90s led to the Nobel Prize. So the universe is not only expanding, as we knew in Hubble's time, but is accelerating. And we blame this acceleration on the force called dark energy. And as I'll talk about in a second, dark energy is exceptionally important because it ends up being the most dominant mass energy component in the universe. If mass is equivalent to energy, E equals mc squared in some sense. And so about 3/4 of the universe is actually in dark energy. It is the dominant component of the universe. Dark matter is about another quarter almost. Only 4% of the universe is in the stuff we see, the atoms. So basically, astronomers are taking 4% of the universe and trying to imply the rest. It's pretty impressive. But the dark energy is important because it's so dominant that it will determine the fate of our universe. People are always asking me, what's the fate of the universe? Well, the answer is we don't really know because we don't know enough about the dark energy. This is just 3 different models based on various cosmologies that people have come up with for the dark energy. There's a possibility the dark energy, which is accelerating the universe now, will change direction and will end up in a big crunch. I think the more favored model by most people is what we call indefinite expansion. And that's the idea that the universe will just kind of continue to expand forever. But there's also a possibility that if dark energy continues to get stronger in time, that eventually it will get so strong that gravity will never win and it will tear apart galaxies in what we call the Big Rip. So that's kind of unpleasant. The good news is all of these scenarios are hundreds of billions of years away. So you have to worry about Andromeda and the sun and a few other things before we have to worry about that. Anyhow, the good news is you don't have to wait that long to learn more about dark energy and the first galaxies in the universe because we have great new telescopes coming online. The James Webb Space Telescope is the follow-up to the Hubble Space Telescope. It's being launched in 2021, hopefully. This telescope is designed to study the very early universe. It's designed to look at the objects even further back than the one in the Hubble Ultra Deep Field. And it works at infrared wavelengths, which because of the expansion of the universe, those distant galaxies, their light is now moved into the infrared. So this telescope should actually find the first galaxies in the universe. Let's hope. But it's a small telescope. It's the same size as actually our current Magellans in Chile, which came online in 2000. So by modern standards, it's not that big a telescope. So at Carnegie, where we've been leading the effort, many of you will know, for the next generation big ground-based telescope called the Giant Magellan Telescope. This is a telescope that uses 7 mirrors, each 25 feet across, to effectively form an 80-meter telescope, 80 feet telescope. This is an incredibly large beast. The dome, by the way, is 24 stories high, just to give you an idea of the scale. This is a huge, very, very complicated beast. When it comes online in the late 20s, hopefully mid to late 20s, it will be able to really study those very, very distant objects in extreme detail for the first time and really help us understand how the dark energy has evolved in time and hopefully answer that question. So we're very much looking forward to that. This telescope, by the way, is on our, if I didn't say it, it's on our mountain, the Carnegie's mountain, Las Campanas in Chile. We actually have a lot of progress. And we'll have to have somebody come and give a talk just on that telescope. So at that point, I'm going to end and just say, we've come a long way in our understanding of the universe since Hubble's time. Hubble was looking at objects that were millions of light years away. We now see objects that are over 13 billion light years away. He, of course, knew nothing about dark matter and dark energy. He didn't know really about black holes. So we've really learned so much about our universe in the last 100 years. But what I always like to tell people is that the universe is continually surprising us. And so if you were to ask me, what is the Giant Magellan Telescope going to find? I can tell you, yeah, it'll see the first galaxies in the universe. It probably will do that. But the things it will do that are more important are the things I don't know. Every time you build a new facility and you have new capability, you discover something you're just not expecting. So the universe has many more surprises for us, and I look forward to sharing those with you in the coming decade. Thank you. You want to stand up? Well, I'm hanging off in some weird way, I know. I get a little animated for my own good. All righty. Okay, now we're happy to answer questions if you have questions for me or Marcia. We have mics here on the side. Feel free to come on up if you want. Let's see how we're doing. I know we ran a little late. We started a little late, but you know, it's astronomy. It's worth waiting for. Sure, go ahead.
I have to confess, the title that brought me here, the day, I thought of the day the Earth stood still. You know, in Washington.
And the universe doesn't hold still.
Exactly. My question is, do you have any insights into the multiverse?
Go ahead. Sorry, I asked you a question.
Dilemma, I would say. Thank you.
Do you want to answer that one? You're going to make me answer it because I'm the astronomer. So, you know, there's an interesting question. We know the universe started with a Big Bang, but the question is, were there multiple Big Bangs? Are there multiple universes? And, you know, there's really nothing at the moment that can rule that out. And in fact, I think it's kind of fun to think that we're just sitting in one of these multiverses. So I think the answer is we don't know. There are some experiments being designed that are in theory could show you that the multiverse idea is wrong. But I think we're very far away from that happening. And there's another great theory I'll just ask because somebody always asks me, which of course is the fact that there's people who think that the universe is a giant simulation or somebody's game or something of that sort. And you know what? I have no better explanation for why we had a Big Bang. So if that makes you happy, we can go for it.
Oh, it's a continuation. I mean, when you think about it, it's a continuation of the Earth was once the center of the solar system. Then we got bumped off to the side. Then we were at the center of the Milky Way. Then we got bumped off to the side. Then we weren't the only galaxy. We're one of many other billions. Philosophically, it sort of makes sense that we might be one universe among other universes. Why stop at just one universe?
I've never thought of that, and I love that explanation. I'm going to steal that one from you, Marcia. That's great. That's really great.
With the ability now to launch thousands of small satellites, is there an application of that for doing astronomy instead of launching one or two big Hubble-sized telescopes?
So the answer is yes. In fact, there are some science you can do with a small space-based telescope. But to do the things that you need to do, like the edge of the universe, these things are really faint. You need a bigger telescope, if anything. I should say, though, that you may read in the news, because astronomers are really quite worked up now about a lot of the satellites that are being launched for communication here on Earth. Because a lot of the things like Elon Musk is doing, they're very, very bright, actually, and you can see them with your naked eye. And in fact, it's a problem for astronomy, because we're worried about having light pollution from the sky looking down. That would be a real problem. So there's a whole series. I'm involved on a very big committee with the American Astronomical Society that's looking at this issue. So the answer is yes, small things would be good, but the things that are bright looking down are not good for us.
Hi. So the universe is expanding, and which means everything is getting farther apart. So how do galaxies get close enough together to merge?
That was a great question. I should have said that during my talk. The answer is that gravity dominates over smaller scales, at least in the current universe. And so the reason why, as Marcia showed, Andromeda is coming towards us, and there were a few other objects. Those were the very, very nearby galaxies, because on those scales, gravity is just much stronger than the actual expansion. If the dark energy continues to be strong, however, that will not be the case. And so that's, in fact, the concern in the Big Rip model, is that at some point, gravity won't be able to hold things together. It will lose out to the expansion if it gets stronger.
I think of the universe as being cold, but you kept talking about all these hot spots, hot areas that are billions of light years across or whatever, I don't know. So is there an average temperature of the universe that's speculated on?
Yeah, the average temperature of the universe is pretty cold. It's 3 degrees Kelvin, and that's the remnant radiation from the Big Bang. But I should have started with this. I have a bias here. I'm an X-ray astronomer that somehow ended up running an optical observatory. I have no idea how that happened. And so that's why there was a very big X-ray component to this talk, but that's just because that's what I find interesting. But on average, space is cold and empty. You're right.
It's just an isolated area.
Yeah, that's right. Yeah.
Where there's activity with matter and interactions.
That's right. Yeah.
But space is big, matter is small.
It's so big. You still cannot really comprehend how big an empty space is. I think the galaxy merging where nothing happens is an example of that, right? That shows you just how empty space really is.
Hi, you were talking about the colors of galaxies in the Hubble photo, and you had blue galaxies and the red galaxies had older stars or bigger stars and the galaxies weren't producing any new stars. I'm trying to understand what it looks like, or what does a dying galaxy look like, and as that relates to how stars are formed and then die. And so what does a dead galaxy look like, or what happens?
Yeah, so I should be careful. It's not dead. Those stars will live for tens of billions of years. It'll continue to be red. They'll get fainter over time as stars die out. If you don't replace them with new stars, though, the total energy output of the galaxy will decrease over time, but over a very, very long time scale. This is really tens of billions of years.
But what does it physically look like?
It's just a galaxy. It just doesn't have new stars in it. That's all.
So there's no light from it.
There's no. It'll still be, the red stars will still shine for a while. Eventually, you're right. Eventually, there'll be no light. But the universe hasn't gotten to that point. Those red stars live far, far longer than the age of the universe.
So there hasn't been any galaxies that have.
That's right.
Died.
There are no truly. When I say dead and red, I'm really mean it's not forming new stars. There's no dark dead galaxy, if that's what you're asking. Yeah, that's way in the future. That's way past the Andromeda merger. Way, way, way past.
I have a couple of questions. How close to sit next to the mic?
A little closer, I think.
Okay. First question is on Vera Rubin's discovery of the unveiling of the dark matter around galaxies for the compensation of the speed of the rotation of the galaxies. Has any more work been done as to what that dark matter is? That's the first question.
Yeah, well, actually, you have a book on dark matter, right? Or you want to say, I don't know if you want to comment.
Well, very much. Once Vera presented her data with over 200 galaxies, she was finding this effect. And that, even though dark matter had been discussed before, her great work really brought it up to one of the top mysteries in astronomy. And all sorts of people started trying to think of ways to explain this in different ways. One of the first things was it must be a particle that we haven't yet discovered. And there is in advanced theories of physics, they haven't found it yet, but there's theorized these, what they call supersymmetric particles. And they call them neutralinos that we haven't yet discovered. And particle physicists have been devising all kinds of methods. There are now a number of experiments going on underground to try to find these new particles. So far, I started reporting on this in the 1980s, thinking they would have found it by now. They have yet to find it. It is one of the hardest things for astronomers to figure out. There are other theories, others who think that maybe our laws of physics have to be readjusted, that maybe Newton's laws of gravity change over time and over long distances. That's another theory. So people are coming up with all different ways to try to explain this.
Let me give you a hint. I call that particle hygracium, and it's the particle that makes space what it is. It's a particle that has an attribute of anti-gravity, gravity, pulsating frequencies that enable particles in space to spread out. It's also that gravity, anti-gravity pulse that's the dark matter around galaxies, forcing the galaxies to rotate at the speed. So gravity is a push and a pull. We discovered, of course, that in space, if you take the same gravity equation and apply it to spheres in space as a push factor, the same results come out as a pull factor. So space is the energy that provides the rotation, much like an alternating current on a permanent magnet creates a rotation of that rotor.
So I'll just comment that there are theories that space itself may have some sort of component, but that is actually more for the dark energy. So in fact, a lot of the dark energy models do imply something very similar to what you're suggesting.
Right, and I call it a cosmological balance.
Yes.
It's a book I wrote. Anyway, the second question I have, is if there's so much dark matter and gases in space, why do we continue to say the redshift is a result of speeding galaxies away, rather than the material between the galaxies and us that's causing the redshift?
Well, no, you're right. Because we observed the galaxy redshifts. That's why. That's an observed fact. Hubble didn't, as Marcia said, Hubble he didn't explain that the space was increasing. He just showed there was a relationship there. What we observe are the galaxies. But you're actually right. It is the fact that space is being created that is actually causing that.
And as you said, Einstein was adamant about keeping the cosmological constant to balance his equations.
Well, he wanted a static. Yeah, that's a whole other story. Actually, probably book. We'll do one more question, and then if there's other questions, we're happy to come up and address them. Go ahead, sir, right here.
Yeah, I think he touched on kind of what I was wondering about. A couple of things. One, this balloon analogy of the expansion. Where did that come from? Second, it's hard for me to understand that, except I listen to that guy. Maybe that's somewhat of the explanation. The other thing, does dark matter and dark energy, does that precede the Big Bang? In other words, that was there before the Big Bang?
So on that question, I don't think we know. And I always say, go ahead, sorry, was that the end of your...
That's all right,
yeah.
Go on, go with
what I would say is we really don't know what was there before the Big Bang. And that's why I'm happy if it's some guy on his computer simulating the universe, and that's why we're here. Hello, I hope that's fine with me, because we really have no better explanation. Okay. The first question, now I'm trying to remember I had an answer to it, I don't remember what it was.
The balloon. I think Arthur Eddington may have been the first one to have done that back in the 1920s, but it does give a somewhat wrong impression.
It does. I was going to say it's a terrible analogy.
Yeah.
It is. The problem is your brain cannot wrap around the expanding universe.
Right.
Because everything in your universe occurs within space. And so when you think of a balloon, you're thinking of it being in a bigger space, right? It is the space itself. And so our brains can't really, in my mind, I always tell people, do not spend endless hours worrying about this. Because your brain can't really comprehend it in that sense. It's the space itself that's being created.
In each position and point, it is expanding.
That's right.
It's expanding here, it's expanding
over
there.
That's right. So in fact, that analogy is just to point out that everything is moving away from each other. That's the reason why that balloon analogy works, or the raisin bread analogy works. Yeah. It's to demonstrate that, but it's not really right as Mark.
Well, it also brings up the question that I always get at lectures is, what is it expanding into?
Yeah.
And that's where I have to say...
That's what I usually ask.
You can't, because you're once again thinking of it in space.
Right. Well, thank you. This is disturbed
Just
my...
don't stay up at night worrying about that. There are many more important things.
That's my comment, that this has been disturbing my sleep for years.
I get that all the time from people. Yeah. All the time from people.
Now, one other thing quickly is, since matter is, as we know it, the regular matter, is such a small percentage of everything, then it's highly likely that all our physics that's based on a lot of that stuff really is just tentative.
Well, I think we know how gravity works, and dark matter works under gravity. That's how we know it exists. We clearly do not have a complete understanding of physics because we don't understand the dark energy. And as I said in my talk, I'm sure we have many things wrong. I always will say that. I can look back at my own papers from 25 years ago and go, oh my gosh, what did I can't believe what I thought in 1994. And that's part of science. And I think as a scientist, you just have to accept that. I don't mind. I mean, I know Edwin Hubble never wanted to be wrong. I don't really care if I'm wrong. If I've actually learned something more, and I'm happy to admit when I'm wrong. So, but I think. Thank you. So, We're happy, Marcia and I are happy to answer more questions if people want to come. I want to remind everybody we start the series up again here in February. So you'll be getting a notice about that probably in the new year, I suspect. Let's thank Marcia for coming down from Boston for this wonderful talk. Thank you.
Thank you.